Okay, good evening, everyone. This is the eighth tutorial session for the NPTEL course on variational calculus and its applications in control theory nanomechanics. I am G.R. Krishnansan Avatar, a PhD candidate at the Department of Aerospace Engineering in the Institute of Science. So, keeping up with the template that we had set out at the very beginning of the first of the tutorial sessions, I will start with reviewing some of the important concepts for the week 9 of this course, since in this tutorial session we are going to cover portions of week 9 of the course, and then I would be reviewing or solving some questions. So essentially the template is we'll be reviewing the topics. We'll start with second variations, and then we would move on to describing or briefly describing two conditions that are aimed at determining the stability, so to speak, uh, of the variational problem that we are looking at. And then we would end the discussion, or the last topic would be optimal control theory. And once we have reviewed that, we'll start with solving a bunch of problems. Okay, at first let's describe. I'll just be reviewing some of the things that we had discussed in the last tutorial session. We had started with the need for second variation. It is what you may have noticed is the Euler-Lagrange equation is essentially the first variational derivative of an variational problem that we are looking at. And it essentially just gives us the necessary condition for the existence of extremum of a functional. And mind you that it is not a sufficient condition, and which brings us, which essentially tells us the need to determine the second variation of a variational problem. Let me just briefly review the finite dimensional case. Here, the necessary condition to determine the extremum of a function f is equal to f of x1, x2 till xn. The necessary condition is that grad of f is equal to 0. And this gives us our stationary point x vector is equal to x naught vector. And to determine the nature of the stationary point, we require this is what we call as the sufficient condition. And the Hessian matrix is for which we require a Hessian matrix, and it is defined as second derivative of f with respect to x, xi, and xj. And h is definite. This implies that this means that f has a local extremum at x naught vector, and h is indefinite, means x naught vector is a saddle point. Okay. Now let's take a look at the second variation of functionals. Now, given a functional j is equal to x naught to x1 of f x y y prime, and where the end conditions are y at x naught is equal to y naught and y at x1 is equal to y1. The first, and then we introduce something called the first order perturbation, which is y vector is equal y hat is equal to y plus epsilon eta. And mind you that both functions y and eta are smooth functions, and here epsilon is a small number, which essentially determines the amount of uh, or the degree of perturbation that we introduce into the extremal, which is supposed to be y. Now, given that our functional j is, I mean, the integrand of the functional f is a smooth function, and then of x, y, and y prime. So if we introduce a perturbation epsilon into that integrand, this will this will still retain the smoothness for the integrand f, and thereby the smoothness of the functional j with respect to epsilon. So using Taylor series, we have this j of y hat minus jy is equal to epsilon delta j eta y plus epsilon square by 2, and del square j eta y plus order of epsilon cube terms. Okay, and and then we have these two condensed expressions, which are uh, del j eta y. This is defined as x naught to x1 of eta del f by del y plus eta prime del f by del y prime. And then the second variation, which is del 2j is equal to x naught to x1 eta square del square f by del y square plus 2 eta prime dou square f by dou y prime plus eta prime square dou square y by dou y prime squared, and integrated over dx, integrated over x. Yeah. So suppose j has a local extremum at y. Then for this, what does it? This implies that, uh, and then we essentially want to know the nature of the extremum at that x for that extremal y. Then we have two scenarios, or ideally we have three scenarios. But right now let's discuss the first the two, which is minimum and maximum. So say if del square j is greater or equal to 0, then this implies that y is local minimum. And mind you that is equality. If the equality will simply mean that this is not very determinate, in the sense that if the second variation is exactly 0, then we can't say that it's strictly local minimum. And likewise, del square j is less or equal to 0. This implies that y is local maximum, but not strictly local maximum. For it to be strictly local maximum, we need to have the strict requirement of del square j is less than 0. Okay. Now let's talk about Legendre condition. So Legendre condition is this essentially tells us what would be. So suppose the functional j has a minimum, local minimum at the extremal y, then what is the requirement for that? So the statement here says that this is essentially a theorem, and it says that let j be a functional j of y is equal to x naught to x1 f of x y prime dx, where f is a smooth function of x y prime. Now suppose j has a local minimum at y, then f y prime is greater or equal to 0 for all x is an element of x naught x1. So the requirement that you clearly see is, so this is the requirement. This is the requirement. Okay. That the second partial derivative of f with respect to y prime should be greater or equal to 0. And this should hold for all x lying in the interval x naught x1. And mind you that Legendre condition is a point-wise constraint, in the sense that this is a point-wise, not constraint, it's a requirement, and it has to be satisfied point-wise at every point x in the interval. And then the thing is, we would require a more exhaustive, or I should say something which is global in nature, a condition for for the existence of extremum, which is more global in nature. So there is where Jacobi condition comes into the picture. Now let's start with what do you mean by this. There is something called the Jacobi accessory equation, and this is when this is that given by the differential equation. And mind you that this is for the functional that we had just talked about. For this functional, this is our functional. So for this functional, the Jacobi accessory equation is d by dx of f y prime into u minus f of double derivative with respect to y minus d by dx of f y prime, and into u is equal to 0. Now the conjugate point. Now, so essentially we have to solve this differential equation, and what we clearly said that this equation is linear in U. So we solve this differential equation to obtain U. Now let me talk about something. This conjugate point, and this conjugate point has a major role essentially to has a major role in deciding the nature of the extremum. So let's have a point kappa. It's an arbitrary point, and I would say that it's a variable point which needs to be determined. So let kappa is an element of the real number minus x naught. So we exclude x naught from the set of real numbers. Now, if there exists a non-trivial solution u, so the non-trivial solution means that u need not u is must not be equal to zero everywhere on x naught on x, which is an element of the interval x naught x one. And then this, so we are if there exists a non-trivial solution u to the Jacobi accessory equation that satisfies u x naught is equal to u kappa is equal to zero, then kappa is called conjugate point to x naught. Okay. So we know the definition for conjugate point, and then we talk about the Jacobi necessary condition. No, and then we'll talk about both this necessary and sufficient, the condition for sufficiency. So the theorem says that given y is a smooth extremal for functional j of y is equal to x naught to x1, fx y prime says that for every x is an element of x naught x1, we have to meet. This is what we call as the strict uh, or the strict Lozandre. Uh, okay, so the sufficiency condition. The Jacobi sufficient condition says that let y be an extremal. Okay, so it says that let y be an extremal for the functional jy, and then okay. Before that, let's describe. I mean, we are talking about Jacobi necessary condition. So if y f y prime f double derivative of f with respect to y prime greater along y, if y produces a local minimum for root j, then there are no points conjugate to x naught in the interval x naught x1. And later we'll talk about how to determine the conjugate points. And the sufficient condition says that let y be an extremal for the same functional, and then along this extremal we have the strengthened Legendre condition is satisfied. Now suppose that there are no points conjugate to x naught in x1, x naught in this one, then j has a weak local minimum at y. So this we have Jacobi necessary and sufficient. The necessary condition as well as the sufficient condition. Now let's review the convexity condition. So a smooth function f is equal to fx y prime is convex if and only if for each y prime is an element of omega is a subset of R2. And the conditions are that double derivative of f with respect to y is greater or equal to 0, double derivative of f with respect to y prime is greater or equal to 0, and f y into f y prime minus f square y prime is equal to delta is greater or equal to 0. And now let's review the concepts in that we had discussed the in the week 9 of the course, and this is about optimal control. I'll just give a brief explanation of what's an optimal control. So, optimal control problem is to determine the optimal control U star T, which causes the linear or nonlinear time invariant system, whose governing equation is, or whose evolution equation is given as x vector dot is equal to f vector, which is a nonlinear function of x vector, u vector, and t. And this is also what we call as the evolution equation for for a plant. And then what it does is the problem is to determine the optimal control U star for the plant this system x dot is equal to f vector to give the state x vector dot sorry x vector star that optimizes the general performance index. So we construct a cost function. So j of the functional jy here is we call it as a performance index, or even in optimization, if we use optimization terminology, then we can call this as the cost function. So we have this general performance index equation, which is given by j of y is equal to s x t f, and tf, mind you, is the final time. Uh, so we have some final time factor, uh, and then something which has to be optimized over the entire time. Okay, and with some constraints on the control variable u vector t and slash or x vector t. Okay, so ideally, what we do is the problem is to determine the extremum of this functional subject to a system evolution constraint and also some constraints on the u vector and or even the state vector, which is x vector. So this is what our optimal control problem is going to look like. Okay. So by now, if I just give a quick recap of what we have just discussed or reviewed. So we started with the need and necessity for second variation before moving on to discussing this an analogy for the second variation in a finite dimensional optimizing problem. Then we followed it up with the derivation, or so to speak, the expression um, for the expansion of the functional in terms of the perturbed quantity using Taylor series, and then laid down the conditions for to describe the nature of a local extremum at for any extremum or extremal y. Then we talked a bit about the Lausanne equation, and then and the Lausanne equation, we said that for an extremum to be minimum, or to be a local minimum, we need to satisfy a condition on the integrand, which is that the double derivative of f with respect to y prime is greater or equal to 0 at every point in the interval. So this is what is the key here. Okay, and then we talked about Jacobi condition, and mind you that Jacobi condition very much depends on uh, the, the existence of conjugate points, or existence of non-trivial conjugate point. Okay, that to be more precise. So to do this, we require to solve the Jacobi accessory equation, and which is a linear equation in the variable u. And once we obtain the variable u, then we have to um, try to locate a conjugate point or try to determine a conjugate point with for at the first we'll assume a conjugate point and we'll see whether that really is true or not. Once we have the conjugate point, and based on the location of conjugate point, whether it lies within the interval x0 x1 or outside, if it lies within the x0 x1, then it will see that the extremal that we had determined is not local, is neither we cannot beforehand we cannot tell what you call the nature of the, I mean, that extremal is neither a local minimum or nor a local maximum. So that's what we can say very clearly. And then you will see that both the Jacobi necessary and sufficient condition is based on the existence of the conjugate point itself. Okay. And finally, and then we had also talked about convexity condition. And the thing is to determine whether a integrand or the functional is positive definite or not for a functional or for the integrand to be positive definite. Mind you that if the function is positive definite, then the existence of a local minimum is guaranteed. Okay, and then to define the nature or to determine that nature of whether that it's a convex or not, we require to satisfy some conditions which are given here. This is that the double derivative of f with respect to y is greater or equal to 0. Double derivative of f with respect to y prime is greater than or equal to 0. And fy y uh, and into y prime minus fy y prime square is equal to delta is greater than 0. Okay, and then we follow it up with optimal control. Okay, and here we had talked about the need of the how we define optimal problem, and then also talked about the form of an extremal of the optimal control problem. Okay. Now we should begin solving some problems. Okay, let's. So at first we'll review two questions from the previous session, and both of which are based on second variation. The first question says that let j of y is equal to, and mind you that this already I had already solved in the previous session. J of y is equal to x0 to x1, 1 plus y square by 1 y prime square dx. Suppose that j has a local extremum at y. Use Laurent condition to determine the nature of the extremum. So Laurent condition is partial derivative of f with respect to y prime squared is greater or equal to 0 for local minimum at extremum y. So we find the first derivative of f with respect to y prime, and again the second derivative. And what we see is, so this is our second derivative of f with respect to y prime. And we see that the numerator is also greater than 1, greater or equal to 1. Uh, and for a non-trivial y prime, in that case, then the entire quantity is greater than 0. And so this means that the j of y has a local minimum at the extremum y. Now let's move to the second question in this. Here we are solving geodesics on a sphere of radius r is equal greater than 0 corresponds to the extremals of a functional disk j phi, and where phi is the polar angle and theta is the azimuthal angle, and theta phi prime is equal to d phi by d theta, so that j satisfies Laurent condition. So we start with the integral with the integrand. We first difference with respect to phi prime, and then differentiate again with respect to phi prime. So what we see, this is a final expression. Okay, let me check. Okay, so what we see here is that there's a numerator. Okay, um, okay, the numerator is going to be greater or equal to 0, 1 plus signs, and then the denominator is also greater or equal to 1. So essentially, what we have is that the second derivative or with respect to phi prime is greater or equal to 0. And for local minimum at to exist, we see that f of phi prime is greater or equal to 0. This means that our Lausanne equation is satisfied. Okay, let's have a third question.
Can you find the extremals for J and show that for the fixed endpoint problem, this extremal produce weak local maxima?
Okay, so what's the expression for the functional j? So
J small bracket y close small bracket.
and so this is equal to 0 to pi by 4, and y prime minus y prime squared minus 2y
2y.
cosine hyperbolic, yeah, cosine hyperbolic dx. So
Yes.
this, okay, Okay, so what we have here is that given this functional, we need to find extremals for j and show that for fixed endpoint problem, these extremals produce weak local maxima. Okay, so what we'll do is let's go step by step process, very much following the diction which is laid out by the question itself. So we first determine the extremals for j. So our first goal is to determine the extremals for j. Okay, and you know very well that for this we require an integrand which is f is equal to y squared minus y prime squared minus 2y cosine hyperbolic x. Okay, and let's determine the Euler-Lagrange equations. Okay, and the Euler-Lagrange equations are given by d by dx of del f by del y prime minus del f by del x is equal to 0. Okay, and then this implies that d by dx of del f by del y prime is um, 2y sorry minus 2y prime minus of 2y minus 2 cosine hyperbolic x is equal to 0. Then what we'll do is we'll just factor out minus 2. So we'll have y double prime plus y is equal to cosine hyperbolic x. Okay. So this is our equation to determine the extremal. Now what you see is this is equation which is second order ODE and it's also second order inhomogeneous or no inhomogeneous equation or non-homogeneous equation. It's a second order inhomogeneous ODE, right? So you know the drill, right? That to determine the solution, we need to determine its particular and the homogeneous equation. So I'll just move to a new slide. Okay, so our equation is y double prime plus y is equal to cosine hyperbolic x. So let's first start with determine homogeneous equation. So y of x is equal to y homogeneous x plus y particular x. So for homogeneous, what we have is y h double prime plus y is equal to 0. So going by the expression, the general solution is yx is equal to a cosine x plus b sine x, right? And this is our homogeneous equation. For particular equation, we need to solve yp double prime. There is also fx plus yp of x and cosine hyperbolic of x. Now what we'll do is we'll assume a particular form of the equation as yp is equal to a c into, or better I'll just write as p into cosine hyperbolic x plus q into sine hyperbolic x, right? Upon substituting this to here, what we have is this implies that p into cosine hyperbolic x plus q sine hyperbolic x plus p cosine hyperbolic x plus q sine hyperbolic x is equal to cosine hyperbolic x, right? And then with this, what we have is 2p cosine hyperbolic x plus 2q sine hyperbolic x is equal to, not 0, is equal to cosine hyperbolic x, right? And then comparing the coefficients of, comparing uh, coefficients of p and q on both sides. Not sorry, it's yeah, our goal was to coefficients of cosine hyperbolic x and tan hyperbolic x on both sides. Okay. And now what we'll see is, and then what we see is 2p is equal to 1 and 2q is equal to 0. So this simply means that p is equal to half, q is equal to 0, right? So our particular solution is substituting it here. Putting here, you get as yp is equal to half of cosine hyperbolic x, right? So therefore, the solution is y of x is equal to uh, I'll just call this c1. You'll see the y it comes handy later, and this integration constant as c2. Y of x is equal to c1 cosine x plus c2 sine x plus half cosine hyperbolic x. Okay. So we have obtained the general family of extremals. Okay. And now our goal is to determine, as the question says, that these extremals produce weak local maxima, right? So what we do is, but to do that, we first need to solve the, we need to satisfy the Jacobi's necessary and sufficient conditions, right? So I'll just say that our heading will go as, let's check for maxima. We first, and we had very much, we recall that to satisfy the Jacobi necessary condition and sufficient condition, what we had seen that we first, that the integrand f has to satisfy the Legendre, that strengthened Legendre condition, right? Which is strengthened Legendre condition. And in this case, it is f y prime. Y prime is so let's take a look at the integrand. So the first derivative with respect to y prime is minus 2y prime. Second gives us minus 2. So this is minus 2. And this is less than 0 through what? So you see that we are somewhere moving along, that the extremal is a local maxima line, right? But we are not yet sure of that thing happening. So now what we do is now we have to solve the Jacobi accessory equation. However, we saw that the independent that the Jacobi's accessory equation is a linear equation. So, and it's also second order in nature. So which means that we'll have two independent uh, solutions, and which is I'll just write that the solutions to the JAE can be found can be found out as, first will be u1 is equal to del y by del c1, and which gives us cosine x, right? And u2 is del y by del c2 is equal to sine x. Right. So the general solution is a linear combination of to the JA is u of x is equal to alpha u1 of x plus beta u2 of x. And mind you that alpha and beta are again constants which are need to be determined. And then we have alpha cosine x plus beta sine x. So this is the solution to the Jacobi accessory equation, the general solution. Now let's say that suppose kappa is conjugate point to x naught is equal to 0. And which means that let's check. And then for now, our kappa can belong to anywhere on the real line except at x is equal to 0. Fine. And what we see is that at conjugate point, the value of u has to be 0, right? So first we'll have as x naught, u of x naught is equal to 0. Then this implies that in x naught, you very well know that x naught is 0. So this means that alpha into cosine x, so alpha into 1 plus beta into 0 is equal to 0. Fine. And the second is u at kappa is equal to 0. And kappa, we don't know the value yet, so we'll just write as alpha cosine kappa plus beta sine kappa is equal to 0. Okay, now let's construct a matrix equation. Using this, we can construct a matrix equation such that we are solving for alpha, beta, and this is a homogeneous equation. We'll have 1, 0, cosine kappa, sine kappa, right? Okay. Now for this homogeneous equation to have a non-trivial solution, so the trivial solution alpha, beta is equal to 0 is always possible, but then u is equal to 0, right? And that's not a non-trivial solution, that's a trivial solution. Which means the determinant has to be 0. So this implies that for non-trivial solution to what? To alpha beta, we must have determinant of 1, 0, cosine kappa, sine kappa is equal to 0. So this means that 1 into sine kappa minus 0 into cosine kappa is just sine kappa is equal to 0. Let's move to the next slide. Okay, so which means that we have sine kappa. Sine kappa is equal to 0. Okay. So what we have is we have a sine kappa is equal to 0. And you know very well that this simply means that kappa is equal to 0 plus minus pi plus minus 2 pi. Likewise, it goes till n, yeah, till plus minus infinity into pi, if I say that. Okay. Now, what we see, what is notice here is that kappa is equal to 0 is not permissible because x naught is equal to 0. So beyond this, the admissible kappas are plus minus pi, plus minus 2 pi, and the likewise. Now, let's take a clear look at our interval. Our interval is 0 to, and when we have a look at the function, it goes 0 to pi by 4, right? 0 to pi by 4. And you clearly say that no kappa lies in this interval. So which means that there is no conjugate point to x naught is equal to 0. Okay. So and then from the Lausanne condition, what we see is minus 2 is less than 0. So we had say that we are going along the local maximum line, and now we are very much convinced that the functional has a from the Jacobi sufficient condition has a weak local maxima. Right. So with this, we have solved this problem. Now let's solve another problem in in the same fashion. So the problem is that let's just take a look at the one of the geodesic problem that we have solved today. So we would be expanding this particular problem, extending this problem uh, to determine the conjugate points. So let me write the problem that j be let j is equal to as of phi theta naught and theta 1 root over 1 plus sine square theta and phi prime square into the theta, right? And this is actually a geodesics over a sphere, and here phi is polar angle. And polar angle simply means that the phi is an element of 0 to pi. And theta is azimuth angle. I'll just write as theta is azimuth angle. And you very much recall from spherical coordinate system that theta is an element of 0 comma 2 pi, and it's open on it closed on 0 side and open on 2 pi side. Okay. And here phi prime denotes d phi by d theta. Okay. Now what we are given is that the extremals for j satisfy the implicit equation. And the equation is tan theta cosine phi plus c2 into tan c1. Okay. Where c1 and c2 are constants. Okay. And we have to find general solution to JAE. If A is the point with spherical coordinates r phi naught, theta naught, we are to show that points conjugate to A have coordinates r phi naught and theta naught plus minus phi. Okay. Okay. So we have a very long question, but we won't have as long the answer. So let's begin with the solution. So we have the extremal, we have the implicit equation for the extremal. So let me just call this equation as p into p as a function of phi theta c1 and c2, and this is given as this is just some surface equation, right? Hypersurface equation to be more precise, minus 10 of c1. So this is how what it looks like. Okay. Now let's determine the general solution to Jacobi accessory equation. Okay. And what was the Jacobi accessory equation? Hmm? So the accessory equation we know very well. And for that, as I had mentioned before, that it's a linear equation in U, and it's also second order in nature. So we'll have two linearly independent equations or solutions. So here, the linearly independent solutions are U1 is equal to del P by del C1 is equal to minus sec square C1, and U2 is equal to partial P with respect to C2 is equal to tan theta minus sin phi plus C2. Okay, and this will simply call as minus of tan theta into sin phi plus C2. Fine. Now we'll construct our general expression for the solution to the Jacobi accessory equation, which is u alpha x is equal to alpha into u1 of x uh, plus beta of u2 of x. And mind you that in both the equations we have this minus coming in, and this we can easily absorb in alphas and betas just using just abusing notations. It helps us simplify the process, right? So alpha is x squared plus beta into tan theta into sin phi plus c2. Fine. Because the linearly independent solution doesn't care if it's positive or negative. Okay. And that positive and the negative sign gets absorbed in the constant, the the multiplying factors that we have used, which are alpha and beta here. Now let R phi, phi kappa theta kappa be conjugate point to R phi naught theta naught. Now, from the theory of our conjugate points, what we have is U R phi naught theta naught is equal to 0. So this implies that alpha sec square C1 plus beta tan theta naught into sine phi naught plus C2 is equal to 0. And at the conjugate point, which is U at R phi kappa theta kappa is equal to 0, implies that alpha sec square C1 plus beta tan theta kappa into sine phi kappa plus C2 is equal to 0. Okay, isn't it? Now we'll construct our matrix equation again. And mind you that it's a homogeneous matrix equation. So we'll have sec square C1 uh, tan theta naught sine phi naught plus C2 and sec square C1 tan phi theta kappa sine phi kappa plus C2 into alpha beta is equal to 0, 0. Again, for non-trivial solution, the determinant of the matrix has to be 0. And we'll write it as delta is equal to sec square C1. Mind you that sec square is sec square C1 is common to both the terms. So we'll have sec square into tan theta k theta kappa into sine phi kappa plus C2 minus tan theta naught sine phi naught plus C2 is equal to 0, isn't it? Now, when we take a look clearly, what you see is either the sec square C1 has to be 0 or the term within the square brackets. And mind you that sec square C1 cannot be 0, right? Because then it would mean that U1 is equal to 0, and then there is not a that was not a feasible that's not a non-trivial solution to the or the non-trivial linearly independent solution of the Jacobi accessory equation. So which means that the first term cannot be 0. So this cannot be 0 since U1 cannot be 0. Fine. So our other possibility, the only other possibility, or the only other conclusion is that the term in the square bracket has to be 0. For that, what I'll do is let me uh, bring it to the next slide. I'll just copy this from here. So this has to be 0. And then okay. So it means this is our conclusion from that equation. So what you see here is, now let's make some deduce some things from here. The properties of the trigonometry. Let's just take a digression. Now you know that sine of any say argument, let's call it as psi, repeats after every or I'll just call it that repeats. Not to make it complicated, I'll just say that the psi has a period of 2 pi, right? I'll just call it that sine psi plus 2 pi and into n. N is an integer, right? So n is integer is equal to sine of psi. So this means that sine has a period of 2 pi. For tan, what we have is the one thing about tan is it has a period of pi n because for and again is an integer. So say psi plus pi is will be a will be tan psi. Okay. So this means that tan psi has a period pi. This was the digression, and we'll require this in our in this solving the question here. Fine. Now what you see is, mm, which means that if we are looking at this term here, now let's do it term by term. So sine, the difference between say theta naught and kappa, and for it to be equal, say sine. Okay. So what I'm trying to say is that we cannot have theta naught, that phi kappa cannot be uh, say pi naught plus minus pi, right? Well, the thing is, just let me just take this out. Say I'll take sine phi k plus c2 and also sine phi naught plus c2. Now you see that pi kappa is equal to phi naught plus 2 pi. Is it possible? No. Why? The thing is, if you want these two terms to be equal, then is this feasible? No, right? Why? Because phi is polar angle, and what did I say about polar angle? That it can lie only between 0 and pi, and including both the ends. So what you see is that this is not possible. So the only conclusion is from here is, for this to be equal, we have phi kappa is equal to pi naught. And also you'll see that even we cannot even have phi k is equal to pi naught plus pi. This is also not feasible because this also doesn't lie within the range of phi or the values with which phi can take. So this is done already. So this is already concluded. Fine. Okay, now let's take a look at tan theta k. Okay. And here we see that Let's equate both of them. Now you see that we can have this as theta naught plus kappa plus pi, right? Isn't it? Because it does have a periodicity of pi, doesn't it? And you can see it very clearly from this relation here. And so this is a valid expression. And we can also have theta naught minus pi. Why? It also follows from here that n can be any integer from here. So which means both are valid. So what we can say is that the conjugate point, and this is, remember, this is trivial. Here it is theta kappa is equal to not plus minus pi, and this is non-trivial. So what can we conclude from here? So we can conclude that, I'll just move some parts so that I can write the conclusion here itself. Because it's just one line we have to write, isn't it? Also move things up a bit. I'll highlight this in a different box color because it's not related. I mean, it's a slight digression. Okay, so I'll move everything upside. Fine. So essentially our conclusion was that this implies that R phi naught and what was that? Um, theta naught plus minus pi are the conjugate points to what? R phi naught theta naught. Okay, so this was the thing that I wanted to show here. Okay, now let's solve a few problems in let's also solve one problem in the convexity convexity condition. Okay, solve one problem in convexity condition. So show that the functions root over y squared plus y prime squared and e to the power y are convex. We have to show this. Okay. So we'll take a look at our convexity condition. Let's just go back and have a look. So we had to require that double derivative of f with respect to this. Okay, so we have this. Now let me come back here. So let's pick up the first okay, solution. So the first is uh, f is equal to root over y squared plus y prime squared, isn't it? So the first f is del f by del y is equal to 2y into 2y plus y prime squared, isn't it? And this is y squared plus y prime squared. Second derivative of f with respect to y squared is, well, now we'll have to use that u by v rule. So the first thing is uh, root over y squared plus y prime squared minus y into y by root over y squared plus y prime squared divided by y squared plus y prime squared is equal to y squared plus y prime squared minus y squared divided by y squared plus y prime squared. But fine. Now let's also take a derivative of del square f by del y prime. So del y and del y prime, right? At first. And this gives us uh, so here what we have is so we use that u let's use the u by v rule. So 0 into the other terms minus y into and this gives us minus y prime, and this there's going to be square root here divided by okay. And this will be very similar to the other problem, other this one. So here I'll just call it y squared divided by y square plus y prime squared 3 by 2. Now let's go by the conditions one by one. Is y f y y great if y y y is this term, and what you see is the numerator is also greater or equal to 0, denominator also greater. So this is greater or equal to. Likewise, f y prime the same is the case here, is also greater or equal to 0. What about f y y prime minus f square y prime f square y y prime? This gives us y square y prime square divided by and this will give us as y square y prime square. Look at this, and then we'll have this is identically 0. So this means that our f is convex. Okay. Now let's solve the second problem. And here f is equal to e to the power y. Okay. And 1 plus y prime square. Again, in this case, we'll have f derivative of f with respect to y is ey root over 1 plus y prime, isn't it? Fyy is again the same. And Fyy prime is e to the power y prime. Yeah, divided by, okay. And then what we have is Fy prime is gives us e to the power y prime divided by 1 plus y prime squared, and Fy prime y prime. Let's look at this. This is going to be a tougher job. I mean, relatively tougher job. So this is 1 plus y prime squared minus y prime into y prime by 1 plus y prime squared divided by no square root here, so we'll have just 1. So this gives us e to the power y into 1, so we'll have just divided by 1 plus. Okay, now let's look at the conditions here. Fyy is absolutely greater or equal to 0. In fact, it is always greater than 0. And Fy prime y prime is also always greater than 0. And Fyy prime, and the third condition is the Fyy into Fy prime y prime minus f squared y prime is equal to, so Fyy is e to the power y root over 1 plus y prime squared, and y prime is ey divided by 1 plus 3 by 2 minus Fy prime is e to the power y prime divided by 1 plus y prime squared whole square. So this gives us e to the power 2y divided by, it cancels, we'll have 1 plus y prime squared minus, this gives us e to the power y into y prime squared divided by 1 plus y prime squared, isn't it? Okay, I believe this has another story to tell. And when we take a look at this clearly, let's take a look at the condition again. Because what I see here is that mm, this gives us something like e to the power 2y into, but then we are not guaranteed about whether it's always greater than to 0. Let's look at the calculations again. Ey fine, y prime is okay, ey fine, Okay, fine. So we have is per y. Okay, this multiplies with this gives us fine. So this may or may not be equal to zero, right? I think there is a problem with the question itself. I'll revisit it. It may or may not be equal to zero. We are not yet convinced of the feasibility. So although it satisfies first two conditions, the third is still like something which not is inconclusive. Okay, so let's go to another question. Now let's solve some problems in optimal control. Right? Let's start with the first question. It says that we have a mechanical system which is described by the plant which is x double dot t is equal to ut. What will be the optimal control obtained by minimizing j is equal to half 0 to 5 use u square t dt with the boundary conditions x t is equal to 0 is equal to 2 and x t is equal to 5 is equal to 0 and x dot t is equal to 0 and x t this is also 0. Okay, what's so we optimal problem is j is equal to half 0 to 5 u square t dt constraint x double t t is equal to u of t and x0 is equal to 2 x 5 is equal to 0 and x dot 0 is equal to obviously something here is missing. This is 2 and x dot 5 is equal to 0. Okay, so from j here what we see is that let our f integrand is u square t. So let's first consider an augmented Euler-Lagrange or sorry augmented Lagrangian function. And this I'll call it as L, and this is equal to this would be actually half, so it is half u square plus. And mind you that we have to satisfy this constraint. It looks like a or it is actually a pointwise constraint, right? So it's a non-holonomic constraint, isn't it? And it has to be satisfied pointwise. So what I will do is I will use a lambda, and this we can rewrite as ut minus x double dot t is equal to 0. So plus lambda is a function of t, and this is also a function of t. Okay, and this has to satisfy u of t minus x double dot of t. Okay, so these are like our augmented Lagrangian function. Now let's derive our Euler-Lagrange equation, EL equations. So we have three variables, right? Lambda, u, and x. So we'll have a set of three Lagrange equations. So the first one is for, we see that this augmented Lagrangian function is has a second derivative of x term. So we'll use this del L by del x double dot minus d by dt of del L by del x dot plus partial L by partial x is equal to 0. So then we see that d square by dt square of partial L by partial x dot is minus lambda. Okay. And there is no term containing x dot, so d by dt of 0. There is also no term containing x, so we'll have this is also 0. So this equation is double derivative of lambda by t square is equal to 0. Okay. So the general solution, if we see, then if we solve this, then we'll have lambda t is equal to a t plus b, right? Upon integrating the equation twice, where a and b are constant, integration constants. Okay. Now for the second, what we'll have is minus d by dt of partial L with respect to u dot plus partial L by u is equal to 0. So there is no term containing, there is no term which has u dot. So we'll have first term is d by dt of 0. The second term is uh, ut. I'll just we already know that u is a function of t. So u, and then second is u plus lambda is equal to 0. Okay. So then this means that u is equal to minus lambda. Fine. So we'll have this, we have this. Now what we do is we need to also solve the third Euler-Lagrange equation, which is minus d by dt of partial L by partial lambda dot plus partial L by partial lambda is equal to 0. And you clearly see that there is no term which is with lambda dot. So this implies that minus d by dt of 0 plus, and lambda has term is u minus x double dot, right, is equal to 0. And this is nothing but our plant function, plant equation, right, x double dot is. Now what we see from very clearly is that u is equal to minus lambda, isn't it? And then what? And then so this implies that x double dot is equal to minus lambda, which is nothing but minus of a t minus b. So a t minus b. So upon integrating x double dot twice, so we'll have let's do it sequentially. Let's integrate it first time. So this means that x dot is equal to minus at squared by 2 minus bt plus c, and x is equal to minus a t cube plus 6 minus 5. Okay. So use the boundary endpoints. So x at 0, 2. So this means that d is equal to 2. Fine. And the second is, let's use the second, which is x dot at 0 is equal to 0, right? So this gives us c is equal to sorry, x dot at 0 was also 2, right? Yeah, it is 2. So this means c is also 2. Now let's use x at 5 is equal to how much? 0. So then this means that minus a into 125 by 6 minus b into 25 by 2 plus t into 2. 5 into 2 is 10 plus 2 is equal to 0. Let's just multiply throughout by 6, and so this gives us, and then take terms on the other, I'll take the term on the other side. So this gives us 125a plus 3 into 25 is 75b. 10 into 6 into 12 is this gives us is equal to 72. Likewise, x dot at 5 is equal to 0, right? So then this means that minus a into 25 by 2 minus plus 2 is equal to 0. Then this gives us, upon rearranging, we'll have 25a plus 10b is equal to 4. And this gives us 125a plus 50b is equal to 20. Fine. And you'll know why I'm doing this. Now I'll call this equation 1 and equation 2. So 1 minus 2 gives us 75 minus 50 is 25b is equal to 72 minus 20 is 52. So this means that b is equal to 52 by 25. And then what we'll have is, let me rearrange this so that we have more space. I don't want to take it to a new page just because of one error, just because we need to include one equation somewhere. Now what we do is put this in the second equation. So 125a plus 50 into 52 by 25 is equal to 20. So 2, right? So we'll have 125a plus 104 is equal to 20. So this means a is equal to minus 84 by 125. Now we are required to find the optimal control. So actually all should have been start, because that's what we are, but okay, I'll reserve it for now. So the optimal control is equal to star, and this is nothing but minus a minus b, right? So minus a is 84 and minus b is 52 by 20. So this is our answer. Okay, we'll solve one more last problem for today. So the question says, what is the optimal control u star t of the plant? X dot t is equal to x to t, and then the endpoints here, we have to just find the optimal control in u star. by solving this equation and minimizing the performance index. So what we'll do is we'll only obtain the optimal control in terms of the Lagrange multiplier. So the problem is let's construct our and mind you that we already without going further, I'll just solution is the integrand of the functional is half of x1 square plus u square. Mind you that they are all functions of t. Now let's construct our augmented Lagrange Lagrangian function. And this we have as L is equal to half of x1 square plus u square. And then since we have two state equations, right, x1 dot and x2 dot, and then what we had seen is we'll take the term on the right minus the term on the left. So what we'll have is lambda 1, which is a function of t, into x2 minus x1 dot plus lambda 2 minus x1 plus 5u minus x2 dot. Okay, so we have how many variables? X1, x2, 2, and lambda 1, lambda 2, so 4, and u, so 5 we have. So let's determine our Euler-Lagrange equations. Okay, so first of all, let's start with uh, d by dt of del L by del x dot minus del L by del x 1 is equal to 0. So this implies that we'll have d by dt of minus lambda 1 and minus uh, x1 and minus 2 lambda 2. Okay, is equal to 0. So this implies that lambda 1 dot minus x1, and I'll just take minus on the other side. So 2 lambda 2 is equal to 0. The second is d by dt of del L by del x2 dot del L by del x2 is equal to 0. So this implies that d by dt of minus, sorry, I think I'm jumping ahead of myself. So this will be minus lambda 2 minus x2 is just lambda 1, right? So this means that we'll have, and this is equal to 0. So this gives us lambda 2 dot plus lambda 1 is equal to 0. The third one is with respect to u dot minus del L by. So this means that d by dt of del L by del u dot, which is u dot. This gives us u. There is no term containing it, so this is 0 minus u and plus 5 lambda 2, right? This gives us a 0. So the optimum, and this gives us 5 lambda 2 is equal to 0. And I had told in the very beginning that we are not required to solve this completely. We'll just have u star as a function of t is equal to minus 5 lambda 2 Star as a function of t. So this is the what we wanted to solve for. With this, let's end the discussion for today, and we'll be continuing further. We'll be discussing furthermore as per what will be covered in week 10 of the course about optimal control theory in the next tutorial session, which is the which will be on 4th April. Right? So yeah, so let's close the meeting for today. Thanks.